Translation. When you translate something, you're going to a new language. And so you're going here from the language of mRNA, which is nucleic acids, to the language of proteins made out of amino acids. Translation is the process of decoding messenger RNA into a polypeptide chain or a protein. So we're moving from the language of nucleotides, the nucleic acid language, to the language of proteins, which is made out of amino acids. Ribosomes read mRNA 3 bases, or we call them codons, one codon at a time to make proteins. So 3 bases are a codon. So for example, AUC would be one particular codon made out of 3 nucleic acid, made out of 3 nucleotides. So here's the DNA. This is the strand that serves as the template, and I can even do this, G to C, C to G, C to G, A to U. That's transcription. It's not super hard. But going from RNA to proteins is a little harder. So CGG, I've never memorized this one, but it codes for arginine. UAG, that's codon number 2, that codes for tyrosine. ACC, that's codon number 3, it codes for tryptophan. And you don't have to memorize this. I'm going to give you a cheat sheet for it. But the idea is that this is translation. It's a new language. You're going from the language of nucleotides to the language of amino acids. So what I want to do now are the details of that. So we'll look at ribosomes. Ribosomes are the site of the place where you make proteins. And they have a large subunit and a small subunit. And the mRNA goes right here, right between the two subunits. So they have 2 sites on them for tRNA attachment, the P site and the A site. And the step 1 is initiation. That means to start. So the thing that happens first is the messenger RNA attaches to the small ribosomal subunit. AUG is the start, so you always start with that. And here's that, the cap that you start with. And then the next thing is that the small subunit and the large subunit will come together. So initiation is the beginning. You've got AUG, and the first thing that happens is a transfer RNA molecule comes over. This is made out of nucleotides, just like all RNA. And so you've got AUCGGA, whatever it is. Right here, there's UAC, and this is complementary to this. And that's always going to carry one particular specific amino acid. This thing is called the codon. It's the messenger RNA. This thing, these 3, are called the anticodon because they are complementary. Then you're going to have, oh, and one more thing too, these are hydrogen bonds. They're weak bonds. They don't need to be held together very strongly. Hydrogen bonds. So then another transfer RNA molecule will come along, and these are again complementary. And this one, GAU, will always code for this particular amino acid. And then a peptide bond will be formed. A peptide bond is just a covalent bond between amino acids. So it's a strong bond. Then you see another transfer RNA molecule come along, but the ribosome has to move that way. Or you can think of the ribosome staying put and the messenger RNA moving along that way. So let's see how that works. So step 2 is elongation. As the ribosome moves, new tRNA with their amino acids continue to fill the A and P sites of the ribosome. So this one goes away, but look, the amino acid stays put with the other amino acid that it's bonded to. And so this one moves over. Let me go backwards. This GAU one is going to move over here. So look, GAU has moved over here. A new molecule of tRNA has come in, and you formed a new bond. This one will go away, but the amino acid will stay behind, bonded to the first one and to the third one. So here that one is going away, but the amino acids stay together. Now this one goes over here, the GAA one goes over, and a new one comes in. And so here it is, GAA has moved over one. The amino acids are bonded together, and now they're bonding to this 4th one. Now this one will go away. And then this one will come over here, and that goes on and on and on and on and on. And so we have this long chain of amino acids. I'm showing you the first, second, third, fourth, the fifth one. This means that there's a whole bunch of others that wouldn't fit on here, all the way up to number 199, amino acid, that's AA, amino acid 200. And then you have the terminator, the stop codon, and you're all done. The protein now, the polypeptide, can come off and it will be folded the correct way and you'll have a protein. So step 3 is termination. The end product is a protein. So the end product of protein synthesis is the primary structure of a protein. The sequence of amino acids bonded together by these things, covalent bonds. In this case, because of where they are, they're called peptide bonds. And let me go backwards a sec. Remember, primary structure is the order of amino acids. From here, they'll fold, or they'll coil, and they'll fold on top of each other. Sometimes join another chain. So here's the big picture, from messenger RNA to proteins. So here's codon 1, 2, 3, 4, 5, 6, 7. This happens to be a stop codon. So if you look at the amino acids, 1, 2, 3, 4, 5, 6, you've got 6 amino acids coded for by 6 codons, plus the stop. So 6, 12, 18, that would be 18 messenger RNA nucleotides plus these 3. So there's your primary structure, and I'm just using this picture to show you the peptide bonds. And that video won't work. So let's do a little bit of quiz time. Translation, that's going to a new language, so that's going to proteins, RNA to proteins. Transcription, that one even I can do, that's DNA to RNA, same language. Making mRNA occurs, so you make mRNA from DNA, so that has to happen in the nucleus so the DNA can stay protected. Making proteins happens out in the ribosomes, which is in the cytoplasm. The enzyme needed to make RNA is, making RNA is RNA polymerase. A promoter region is, so pause this and read through them. It is a region of DNA that allows RNA polymerase to start. It promotes it, I guess. The part of mRNA that is kept and codes for a protein. Introns are intervening sequences, you get rid of that, so it's the exons. The part of mRNA that is spliced out and does not code for the protein, that's an intron. For the DNA sequence AAA, TTT, blah, 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 what's the complementary DNA strand? Okay, if it's DNA, I can cross out anything with U's. So now I have to look at this. Opposite of AAA is TTT. I can already tell it's that one. And of course, you should go through and double check, but that's how I would do this one. For the DNA sequence, blah, what is the mRNA strand? Okay, so you know for mRNA, there's no T's. So I'd get rid of these. Opposite of AAA would be UUU. So it's this one. And what's the anticodon sequence? Oh, blah. Okay, so let's write it out. AAA, TTT, CAGG. C. Okay, so that's the DNA. DNA codes for mRNA, which are the codons, which would be UUU, AAA, GU, CCG. And now what it's asking for, though, the anticodons, the tRNA. So U goes with A. Oh, did it really do that to me? There we go, yay. Opposite of A isn't T now, it's U. And then opposite of G is C. Opposite of U is A, G, G, C. So this actually looks exactly like the thing you started with, the DNA, except the T's are used. So that one would be this one. How many amino acids would be coded for by this DNA sequence? We're going to assume there's no stop codons. So that would be 1 amino acid, 2, 3, 4 amino acids. That's a very important question. If you don't understand that one, you gotta come see me. And that's the end of my story.